With 3D printing, you directly go from computer to production, skipping steps that you would need in conventional production. Bringing parts into the physical world introduces tolerances. So how does one measure parts? Wietse knows all about that. Tell us who you are and what you do.
Good day, Neil. Thank you very much, first and foremost, for having me. My name is Wietse, and I am a manufacturing software engineer. I am the owner of Calibras, a company that does digitalization of manufacturing and quality control workflows. Yep. And to put it shortly, my background is a manufacturing background, but I have specialized in data coming from quality control, from metrology, and this is what I'm going to be talking about today. I'm going to talk about metrology, its measuring principles, and the types of data that come out of measuring devices that we use in manufacturing, and how do we approach this data and how do we use them.
Yes, because many of our customers and engineers have used one of these, a caliper. But how does using a caliper differ from the tools that you use, and how do measuring principles relate to that?
So I have prepared couple of theoretical examples on how this actually comes into play. But to put it shortly, the caliper is kind of the first thing that people think about when they think about a measurement in a factory. It is sort of a staple, poster boy, you might say, for a manufacturing engineer to walk around with a caliper and measure stuff. First and foremost, it is one of the simplest measuring instruments, so it definitely falls under the umbrella of metrology. However, it is definitely not state of the art, and it is definitely not providing us with all the different features that we could and all the different types of information that we can extrapolate from a bit more modern data set. To put it simply, a caliper is a 2D measuring system. It is capable of measuring heights, distances, lengths, width, and these kind of types of dimensions. It doesn't give us any information about the surface quality. It doesn't give us any information about the roughness, about the waviness. It doesn't also give us any information about the 3D shape. So it is essentially a 2D probing device. Some other devices that are available to a modern factory are, first and foremost, digital cameras that are taking 2D images of our measurement sample and then extrapolate the data out of that image. Then we have 3D scanners that are using structured light projections, most commonly, to extrapolate the 3D image of the whole workpiece, from which we could then extrapolate much more information, even some primitive roughness measurements. And then, of course, there are roughness measurements, profilometers, confocal microscopes, and maybe last but not least, the CT scanners, which are penetrating the whole workpiece and giving us a 3D image both from the outside and from the inside, which is very useful when measuring assemblies.
Yeah, and you're already talking about a lot of different things that you are able to measure. So a caliper is a 2D measuring instrument, and then we have 3D scanners capturing the 3D objects, of course. When do you choose what?
When do you choose what is, of course, sometimes only a matter of a convenience of what do you have available. However, when we are talking about really a choice of a measurement device, we have to take first and foremost into account the required tolerances that are specified in the engineering documentation itself, which are then, of course, drawn from the functional requirements and in the end what the customer really wants us to control. That being said, we can't really, if our caliper has a designated accuracy of plus minus 0.01 millimeter, then we can't really be sure that we are going to be always hitting that plus minus 25 micron tolerance. So in that case, we will have to choose something a bit more accurate, like a CMM machine, which I haven't actually mentioned in the beginning. And another thing is, of course, the speed of measurement. So if we are dealing with high output and high throughput manufacturing lines, and we are having some dimensions and some features that we would like to control on a pretty much more or less part-to-part basis, then we really can't choose a slow measuring device such as a caliper in this particular use case, and we would have to go for perhaps a monochrome camera with a dedicated lighting on top of the inspection line. So I would say those are the two main constraints. So the tolerances and the speed.
Yeah, because some of the viewers might not even know, but when going from the digital world into the physical world, when you draw something that is dimensioned as 20 millimeters, for example, in the real world, it's never going to be exactly that 20 millimeters. There's always going to be a deviation, and the deviation we capture or the allowed deviation we capture with tolerances, right?
That's absolutely correct, Neil. And I think you gave a great introduction to my presentation on geometrical product specification measuring principles, which are essentially a series of standards that are describing a language to essentially transmit this message that you have just now said and make it something tangible and something more useful in a factory environment.
Yeah, because let's dive into what can we define in the world of tolerances and measuring.
So let's dive into, as you said, how do we essentially transmit the real data, real part and the real dimensions on a part into something that we can describe numerically, and something that we can be a bit more precise and bit more precise about it, that we can communicate on a larger manner. So first and foremost, what we need to talk about before we even diving into geometrical product specification series of standards is, I'm going to say something a little bit about measurement uncertainty. Measurement uncertainty is, I have to say, my favorite concept, favorite scientific concept. Period. At least for me, it is a little bit. I am a little bit biased here, pun intended, perhaps. But it is definitely gorgeous. It is a way to describe statistical distribution of your measurements. It is essentially saying, I have measured this part, either the diameter, either the width, either the height, doesn't matter. Whatever measurement statement I have given, it is not complete without a uncertainty, a statement attached to it. Because uncertainty statement is essentially saying, I am this sure that this measurement result is close to the real value. If I said that this is 10 millimeters, whatever that is, and I said that my measurement uncertainty is plus minus 0.01 millimeter, then in ideal, theoretically impossible measured case, this real measurement value would be somewhere in between those plus minus 0.01 around 10. And how do you actually compute a measurement uncertainty? Well, there are documented ways and traceable standards and procedures in order to achieve that. What you essentially do, you compute the contribution at each step of your process that contributes to the ultimate uncertainty, and that is first and foremost the effect of, for example, environment, the temperature, the humidity in the room in which you are measuring your component. Second is the effect from the operator. So you have to take measurements from multiple operators during the different shifts, during the different times of the day, so you can have a certain statistical spread and see how much these measurements are actually deviating from a person to person that is performing the measurement itself. Then is, of course, then the effect of the as I mentioned, the measurement device, and the effect of the procedure itself. All of those are then you essentially sum them up as a vector. You multiply them with a factor that is just a safety measurement of safety here, to reach to a number, which you then attach to your measurement result. In this case, I took one example from one of my previous work, 1.0, roughly 3 micrometers, which is then saying basically that whatever measurement that I have done in this environment using this instrument on this dimension, I am plus minus 1.03 microns certain that it will be there.
Because can you give some practical examples of how, for example, using a caliper in an office environment has a different uncertainty than a CMM in a controlled production or quality room? What are like the ballpark figures for uncertainty there?
Yes, I can say not really accurate to the top from the top of my head, but I had this uncertainty here that you can see is actually a CMM uncertainty. So plus minus 1 micron is not something that it is a CMM uncertainty with a very small Ruby probe. This is not something that you can achieve with the caliper. Caliper would be more 10 times this at least.
Yeah.
So you maybe at least 10 times in the best case scenario. And the reasons are of course many. The reasons are that the CMM is by far superior, larger, more expensive machine on air bearings with a very controlled movement. And then of course the measurement lab has always been at 20 degrees Celsius, which has a big effect. When you do proper measurements for some statistical process control, you are always required to leave your samples in the lab for them to cool down or acclimatize sort of to the lab environment, so they can be also roughly at 20 degrees Celsius, and you make that kind of a control before you actually approach to the measurement itself. Okay, so the next thing, now we are getting to the real problematics and the real, essentially the beauty of this family of standards. The GPS, or the geometrical product specification, is a development from GD&T, and GD&T is something that more people actually are familiar with and more people actually easily recognize.
Because for the new people, what does GD&T stand for?
GD&T stands for geometrical dimensions and dimensioning and tolerancing.
Yeah,
it is well, at this point already an old family of standards that is doing exactly the same thing as the GPS family of standards does, except it has a little less flexibility, simply because it is old. And we will talk from now on only about GPS.
Okay.
And the GPS is, as GD&T was, a language to communicate engineering tolerances. So essentially, it is a family of standards that has grown from a need to describe the difference between the real world and the digital representation that we have, not only digital representation, but also analog representation, data representation that we have of that real world in our measurement. It is a series of symbols and rules that are helping engineers all around the world to sort of communicate what exactly do they want for this part to look like, feel like, be dimensioned, and fit to the other components. And for that, it defines its matrix models, which is essentially a very complex matrix of standards, which I'm not going to go into too many details about. But what I really want to dive a little bit deeper into is what you, Neil, have mentioned before, that essentially our parts differ when we measure them from their realistic counterparts, essentially. Yeah. And this is what GPS's skin model is all about. It says that all the features on our parts are existing essentially in 3 worlds: in the worlds of specification, in the worlds, and that is the world that is in the drawing itself. That is the ideal world that we have sort of theoretized and imagined as engineers. Another thing is what actually has been made, what actually the machine has spewed out on the manufacturing line. And then the third one is the inspection, because the inspection itself is also a process. It is not a manufacturing process, but it also touches and it also interacts with the part itself. And as you interact with the physical part, you have to use some kind of a physical principle. It can be a touch, it can be an X-ray, it can be a light, but it is not perfect. It will have its own physics behind it, and it will have its own assumptions. So the measurement itself in the end will differ both from the reality of the workpiece and from the ideal specification that had been set on the drawing itself. And this is why we have these. This is why we have these GPS symbols to define different types of geometrical characteristics that we want to control on our parts. And there are many. There are definitely many of those, and I believe many of our viewers are already quite familiar with this. But what essentially these symbols mean is they are describing some kind of a relationship between the ideal specification and what we actually want to measure. And I will take only two of these as an example. One of them would be flatness, and another one would be a 2-point distance. Both of them are strictly GPS characteristics. They are much older, but strictly to transmit the message to our viewers of how do we actually generate these measurement ideas, these measurement principles. So what you can see on the left side of my slide is the flatness. So when you see that symbol for the flatness, and you say flatness 0.2, so 0.2 millimeters, what that exactly means? That means that on that surface where we have this flatness tolerance defined, if you sample a plane, which is here sandwiched in between these two ideal planes, this sampled measured plane has to be 0.2 millimeters. It has to be fully contained inside two ideal planes that are 0.2 millimeters apart.
Yeah,
that's it. That is essentially the essence of the flatness tolerance. In this case, you are ensuring that your surface is not deviating too much. It is not wavy too much. It is not all over the place, because, of course, this surface would have to then fit to something else. A 2-point distance is by far the simplest integral feature defined in the GPS standards, and it is a feature of length, and it is defined as a distance between the two provisionally sampled points that is measured with two perpendicular lines from a median plane, and a median plane is then again defined differently in this matrix model. So this is what GPS is all about. It is a set of chained rules that are always enabling us to always and anywhere in the world to measure things in a same way. That if I measure something here in Denmark and you get my measurement results in Netherlands, that if you take a look at the engineering drawing and then you repeat the same measurement, you should be reproducible. We should get the same result if we have obeyed the same GPS principles and measured under the same conditions.
Yeah, and if I get a technical drawing and I want to review some of these measuring principles, what is your go-to source for the information on how to measure?
How do you measure? So first and foremost, the only relevant source for GPS rules and for the theory behind it would be the standards, and would be the relevant standard bodies. At the top of every country, there is usually a national metrological institute that is always ready to provide consultancy and to provide help with a very let's call them in-depth questions. However, more often than not, the trainings that is provided by the manufacturers of the measurement equipment is more than enough. So their brochures, their documentation is more than enough sometimes to achieve the satisfying repeatability and accuracy.
So to illustrate the measuring, we scanned our manifold or sample manifold with the GOM scanner, and Vice is going to show us how these measuring principles translate into the software and into actual values.
Thank you very much, Neil. As you have mentioned and so kindly scanned the example manifold, I took a liberty to make a couple of example measurements. Let's start with the flatness, the one that we have followed from the slide. And this example manifold, apologies, has quite a thin straight plane on top in between these two screw holes. And if we imagine that there is another counter component in this assembly that needs to fit on this manifold, then we need to define a flatness tolerance there in order for this seal to be tight. Perhaps if we want to ensure a constant gap in between these two components for potential lubricant in between this flatness or this and the roughness measurement on this surface would also be even more critical. But for the time being, let's just talk about flatness. So in GOM Inspect, how you can do it, you can essentially sample a Gaussian plane at the top.
What is a Gaussian plane?
A Gaussian plane would be it would be a plane that has been made by Gaussian fitting. So from the collection of randomly sampled points, you want to minimize something called the least squared value. So you assume that the error in this plane is Gaussian distributed, normally distributed. And now I can't really go into the of the mathematics behind it, but what you essentially have to do, you essentially have to minimize a least square error in this of these points towards the ideal plane, and that will be your Gaussian plane. So if you can imagine us cutting that plane from a side, and these points are spread all over the place, the Gaussian plane will be roughly kind of here in the middle of
yeah.
Which is also that's actually a good point for our topic of the day. That is also an approximation. It is also a measurement. It is also a measurement in the principle. There's also an ideal that we attribute to our real data. It doesn't exist. It is not. It is there only because we agreed this Gaussian plane is going to be good enough to represent this plane for our production purposes.
Yeah.
The second one that I wanted to showcase in this case was just a point to point 2D distance, which is kind of basically a caliper distance in this case.
Yeah, so a point to point distance is basically the metrology version of a caliper measurement.
We could definitely put it that way. Yes, indeed. We fit two planes on both of the sides, and we measure. We assign 2 points on these two fitted planes, and we measure a distance in between them. This distance is internally constructed as a two point distance. We find that there is a median plane which is not visible here in the GOM Inspect that is found, and two perpendicular lines that are intersecting this median plane are then drawn from the point 1 to the point 2 to give us our distance. And essentially, these two planes from both sides of our measurement are essentially what your caliper would get when you press it tightly to both of the surfaces.
Yeah, so I have my manifold here, and it's basically measuring the thickness of that rib that's connecting the two holes, right?
Absolutely.
So if I show it here, it's this measurement. And can you show how that's constructed? Maybe zoom in a bit in the software, and what makes it different from the caliper measurement?
The difference between the caliper measurement is that on two planes, again, both of these planes are Gaussian planes. One on this side, and one.
Yeah, so we basically take into account the entire surface, the outside and the inside surface of that rib.
Thank you. Exactly.
Yeah. Instead of doing it on a single point. But that also means that I can imagine that it's not entirely straight, that on some points it's thicker and on some points it's thinner, right?
That is correct.
So how does that show in the point-to-point?
That is not shown in the point-to-point measurement. The point-to-point measurement is blind to this difference that you have mentioned. In order for us to be able to properly quantify this, we would have to go with for a plane-to-plane distance, which is a completely different measurement.
Okay, and if we go back to like the list of all the measuring principles that you showed, what are like the different categories that these would fall into? So if we have the point-to-point distance and a plane-to-plane distance, and what
Exactly.
are these different characteristics, or what kind of symbol would we see on the drawing?
Exactly. So in this case, for the plane-to-plane distance, you will not be seeing any of these symbols that you can see here, because here I have limited myself only for the geometrical characteristics. So only for the characteristics that are describing some kind of a geometrical relationship between the different sections on the component. But the closest thing that we could have here, no, unfortunately not. Perhaps a parallelism, and again the flatness is somewhat related to this principle, but no, unfortunately not. For this, we would have to dig a little bit deeper into the GPS standards.
Yeah, so the list is even longer than on the screen.
Much longer, unfortunately. This is just the tip of the iceberg.
Like the other one, the flatness is obviously listed here, and that's yeah, maybe we can go back to the measurement and show the flatness again.
Mm-hmm.
Yeah, and that's basically with the Gaussian plane saying, because then we have a value of 0.2.
Exactly. So we have measured 0.2, and I have placed a nominal value of 0.15 because a reason that should be closely related to its functional characteristics.
Yeah.
Yes, the actual measurement here that we have got out from the GOM inspect is 0.2 millimeters.
Cool, and that basically means that the largest of the distance between the highest point on that surface and the lowest point on that surface is 0.2 mil.
Oh, correct. Absolutely correct.
Well, thanks for giving this introduction into to the measuring principles. If people want to reach out to you to learn more on measuring principles and GPS, where do they find you?
They can find me either on the info@calibras.dk. Calibras also has its own website, and you are more than welcome to add me on LinkedIn, and we can take it from there.
Perfect. Thanks.
Thank you very much.
If you want to learn more about measuring parts, reach out to one of our engineers. And be sure to watch our other SliceShow episodes. See you there!